Okay, let's get started. Right, we're going to start. Thank you. Okay, welcome back. Right, so I've, just to save a bit of time, I've pre-written some stuff on the board because I just wanted to address a question that I was asked yesterday because I had to go home and think about it because I don't pay much attention, I must admit, to the Newtonian form. It's not something I spend a lot of time thinking about because normally we use the Gaussian form of the lens equation. But then I was asked, are you still in the front row? The person that asked me whether the Gaussian form is still applicable to if we were dealing with thick lenses. So remember, we've done everything in the so-called thin lens approximation, and if not, how it would be modified. So I just wanted to just address that question since it was asked to everybody. So the answer is yes, this equation is still completely valid as it stands. You don't need to do any modification to that equation. It's just that the formula for the focal length does change. So this term you'll notice that we don't have in our derivation. You can find it done in books. It's not on syllabus for us, but it's just that you have to work through from the beginning just like we did, but keep in the thickness of the lens the whole time. And you get this extra term where D is the thickness of the lens. So of course this term disappears in the limit that D tends to 0, giving us the equation that we have been used to. So as long as you have this formula for the focal length, the Gaussian, the Newtonian form will work as is. What was I going to say? Oh yeah, bear in mind though that this isn't without any approximations. This still is within paraxial approximation. It's thick lens, but paraxial approximation formula. Okay, and where I've just defined how the focal length is actually defined and the D is defined here. I think you said something about that the focal length is different, can be different either side for a lens. I think we have to be careful about terminology here. The F that I have written there and the F that I am using throughout is the so-called effective focal length. There is only one value for a lens, whether it's thick or thin. I think you were probably thinking of sometimes people talk about a front focal length or front focal distance, I would in fact call it, which is that distance, and then you'd have the back focal length or focal distance. But I am talking about this distance, which is the same either side, and of course these distances are equivalent anyway in the thin lens approximation. Just wanted to address that quickly for those who may or may not have been interested. Okay, right, so we left yesterday. And I was about to just talk a little bit more about the sign conventions, just to sort of clarify. I've been talking about sign conventions a lot, saying that I've been using the real as positive, but I haven't really told you or illustrated properly how that works and what that means, and I certainly haven't really told you much about the alternative. So I'm just going to do that briefly. This is really just for your information. Okay, so I'd got to the stage of just sort of describing a little bit that in the real as positive, this is the right equation, this is the one that we've derived. I've sort of adjusted this a little bit just to be a little bit more general. We've always derived it for a glass lens in air, so this, you'll be used to seeing it as n-1. That is what the syllabus says you have to learn, which is why we've done it like that. But if you were to do all the derivation again for general media, so a lens made of material with refractive index N2, surrounded by a medium of N1, this is what you would get. And then I talked about how in the real as positive convention, real objects and real images have positive distances, and real, sorry, did I say real? Yeah, that's what I meant. And virtual have negative distances. Also, radii of curvature are defined positive if such a lens shape in air would give you deviations towards the axis. Remembering that for a converging lens, F is positive, and for a diverging lens, F negative. Right, so here for convex, both R1 and R2 are positive in our convention, but in general, you may get such a shape of lens which ends up being a diverging lens because you could surround it with a medium of higher density, which would then flip the sign just from that term. So that's where we kind of got to, just to remind us. Right, So let's just look at the examples of a couple of examples of how this actually works. So, and the signs that we are going to get out of it in the realist positive convention. So let's just consider a converging lens here. And I'm going to, actually, that's going to be in the way. I'm going to put a little point-like object outside of my focal length. Okay, so we know from what we learned yesterday that what we expect is to get a real image over here somewhere. Okay, so that distance is u, that distance is f, that distance is v. So in this case, we've got a real object, and also u is positive because the real object, and u is greater than f. Okay, which of course implies that 1 over u is less than 1 over f. So if we look up at the formula there, what that is going to imply is that v is greater than 0, i.e. we have a real, what that is indicating in the realist positive convention is that we have a real image. Okay, if I were to do another example, still with a converging lens, but let's pop my object inside instead, okay? I'm instead going to have focal length's over there somewhere. I'm instead going to have a situation where I don't manage to quite converge the light back to the axis, and I will have instead, sorry about the diagram, but instead I'm going to get a virtual image. So let's see how that works out. Again, I have u greater than f. That's supposed to be my u. Sorry about my diagrams, right? So u is now less than f. Implies, of course, 1 over u is greater than 1 over f, and looking back up there, that's going to mean that my v is less than 0. So it's negative, and that, in this sign convention, is always going to indicate that I have a virtual image. Okay, so that's what we mean, fundamentally, by saying we're using the realist positive convention. And the reason I'm using it, I did say it in the, I think, maybe way back in the first lecture, the reason I'm using it is primarily for two reasons. One is that most of the books of this kind of level will use this, so I'm sort of following that. But also for this sort of level, it's actually just quite nice and intuitive. You know, you just know without even having to think very hard whether your image is virtual or real just because of the signs. However, because I have mentioned it and because some of you will have already through school learnt this stuff, and you may have come across or been more used to the so-called geometric sign convention. So I want to say a few words about that, just for those of you who haven't come across it, so that you know, when I talk about realist positive and geometric, you know what the difference is roughly. So the geometric sign convention, so here's my lens, it's just basically a Cartesian coordinate system. You take the x equals 0 position as the position of your lens, and so this is going to be positive x, right? It makes complete sense. Now, I'll return to that diagram and draw a bit more, but let me just write the lens equation that you would see if you were using the geometric sign convention, and notice the signs that I'm putting on here. Keep it general for the refractive indices. So there are two extra minus signs that we don't have. Hopefully, can we still see the other equation up the top? Oh, just. Can you just see it up the top? So two new minus signs. There's one here and there's one here. So first of all, let's talk about why the minus here, first of all. So what you do in the geometric sign convention is kind of sensible, right? You just take any positions or distances that are in the negative x region to be negative, and any positions or distances in the positive x region to be positive. So if I draw a lens, and this is the first surface that my light will hit, so I'll call that R1, that's the radius of curvature for that. This may be the other way round that I drew R1 and R2 compared to the slides yesterday, but this is the right way round to correspond to this equation. Okay, so what that means is that R1 in this convention would be positive, because its radius of curvature is in the positive x. R2 would be negative, and so I must have that minus sign there, because if that's minus, then I need another minus to give me the whole thing positive to agree with the equation that I wrote right up there, okay? So the two conventions obviously physically must agree, so you need that minus sign to make it all work out. And then the other thing is just regarding this minus, where does that come from? Well, let's just look at this portion of the equation. So what I will have now is 1 over v equals 1 over f plus 1 over u. But let's think of sort of, again, of just a converging lens. Let's think of a case where I'm going to get a real image. So I have this sort of thing going on again. This is my light ray. U now is negative because it's on the negative x-axis side, and I'm going to expect v to be positive. Okay, so if u is negative, I might as well write this equation as that, right? 1 over f minus mod u. So if mod u is greater than f, then I am going to get v greater than 0, i.e. positive, and so on and so forth, okay? And if we had a virtual image, we'd have the other way round. U less than f implies v less than 0, and so I would have my virtual image in the negative region of the Cartesian coordinate system. Okay, so that's all it is. That is all the difference is. As I said at the start, if you were going to do very complex problems, you would want to use the geometric sign convention. For our level, just the real is positive is just very nice and intuitive. If you have grown up learning this already, and this is what you're comfortable with, I have absolutely no objections. You can use whichever one you like. The only thing I would just say is probably the examiners in an exam might be expecting you to use real as positive just because that's how it's taught. And so just to make sure that they know that you know what you're doing, if you're going to use the geometric, I would just write a quick line at the top saying using geometric sign convention, boom, right? And then you go, and then it's all fine. What you don't want is the examiners to think that you've just made a sign error, right? You want them to know that you know what you're doing. But I don't care which you use, whichever you feel more comfortable with or are more used to. It's absolutely fine. Right, so we're getting towards the end of lenses. But I just want to do one more thing before we finish up. And that is, we're going to... So far we've been treating a lens as a single object with two curved surfaces, like I've drawn up there, a couple of boards up. We're now just going to look at instead treating a lens as actually two separate lenses. So I'm going to sort of have my two, these are called plano-convex lenses, and I'm just going to bring them together, and I'm going to treat these two lenses separately. But what we're going to see, the reason I'm doing it is to show you that this situation is going to recover the exact same lens equation as if I had treated the two curved surfaces separately. Now, if you have, well, either listened to me in the first lecture or dutifully read the syllabus, you will know, you will know that systems of two lenses are not actually on syllabus. Sorry, they're not examinable. They are on syllabus, sorry. They're not examinable. But such a situation that we're about to do now is considered so trivial. It's basically two lenses, and it's completely equivalent to a one lens problem, that this bit is on syllabus. So just to point that out. Okay. So if I just remind us again of the general, and back to real as positive, and back to glass in air. So I'll just remind us of the general lens equation, sorry, thin lens formula. Right, so that's the case where I have two surfaces of different radii of curvature. So let's first of all look at a lens that looks like that. So a plano convex lens, that is going to be my R1. Can anyone tell me what the radius of curvature of the other side is? Sorry? I heard something. Thank you, yeah, okay. So I'm going to have one, so my lens equation for this lens is that, okay, plus 1 over infinity. Okay. Have I done it right? Okay, so then I've got the other one. I'll call that R2. So we've got 1 over u plus 1 over v equals n minus 1 over r2, describing that lens. So I'm going to assert for now, but then prove it in the next, or sort of demonstrate it in the next couple of slides, that when you put these two lenses together, what is going to happen is that you just add the so-called lens power. And the lens power is just defined as the reciprocal of the focal length, right? So lens power. So this tends to be measured in diopters, if you've been to the opticians and recognise that phrase, but it's equivalent to length to the minus 1, right? So a lens with power 4 diopters would have a focal length of 1/4 of a metre or 25 centimetres. Right, so if that's true, then what I've got here, is that, and let me just make an addition to these. I'm going to call that 1 over f2, 1 over f1. Okay, so if this is true, hopefully you can see that just by adding those two equations, we're going to retrieve the normal lens formula, right, for two curved surfaces. Okay, so why is that true, or can we just simply convince ourselves that that is true, that that's the effect of putting these two lenses together? So it's probably quite intuitive, to be honest, and this first way, I'm going to demonstrate it in two ways, but this first way is probably quite intuitive because it's just looking at the deviation angles. So, so if I first look at the first lens, here's my, hang on, oh, there we are. Here's my line. Does it actually show? Oh, there we are. Doesn't it? Is it sort of fading in and out to you? Sometimes brighter. Anyway, never mind. Is it? Yeah, it's not just me. So anyway, there's my object spewing out some light rays, causing some sort of deviation, and we'll call that deviation angle D1. And then you plonk on the second lens and it goes through a further deviation D2. Remember, we're in the thin lens approximation, so essentially putting these lenses side by side, they're actually in the same place, essentially, right? So it's just D1 plus D2 is going to be our total formula. So this is our, total deviation angle. And then we have to go back to sort of yesterday's lecture or even last week to remind ourselves of the relationship with the deviation angle. So we know from what we did on prisms that the deviation angle looks like that. And you may even remember, so that's the apex angle of the equivalent prism. And that is given by that in the general case, right? Can you remember that when we did the whole derivation, we required that the apex angle be linearly proportional to the height at which the ray strikes over a constant, and that turned out to be the right constant to put there. Okay, so that means that for our first lens then, so first lens, D1 becomes h n minus 1 over r1, and D2 becomes h n minus 1 over r2, and so you add them together to get the total deviation angle, and you get h n minus 1 over r1 plus 1 over r2, and that was also equal to h over u plus h over v, but you might have to just pop back to yesterday's lecture to remind yourself where that came from. You may or may not remember. But anyway, you can see then that what we've done is recover the normal two curved surfaces lens equation. So that's one way of just thinking about it, just think about the deviation angles. The second way is maybe a little bit nicer, sort of mathematically at least, and maybe a nice way of thinking about it as well. And that is to think of it along the lines of that what the first lens does is actually produce, well, okay, as it's drawn here, it produces a virtual image which then serves as the object for the second lens, right? So here we are, here's our original object. The light gets deviated a little bit, produces this virtual image here. This acts as an object to the second lens, and then over here we see the final image, okay? Now, in these diagrams, I happen to have assumed that this first lens is not strong enough to bring those light rays to a focus, i.e. therefore it's a virtual image that's created. But the maths that we're about to do, it doesn't matter. This lens could be stronger. I could have instead achieved a real image, a real image, sorry, and then that would have served as a virtual object for the second lens, but you still overall will get the same result. It's just the same maths that I'm about to do. I just happen to have drawn that particular example. Okay, so what we're going to do, so for the first lens, I mean, it's all on the slide, but I'm just going to sort of do it in real time so that we can see. Here's my lens equation for the first lens. Here's my lens equation for the second lens. And then I'm going to say, well, okay, my actual object is here. So in my final equation, let's just set u1 equal to u, and my final image is at v2, so let's set v2 equal to v. And then the other thing to notice is that v1 equals minus u2. So can someone just explain that and explain the sign for me, bearing in mind we're working in the real is positive sign convention. So why have I set that? Anyone? I think you know. Yeah, go on.
So the V1 is U1 obviously negative 2 in it, and that's starting at your next U.
Yeah. Yeah.
Beginning to the next.
Okay, so V1, what sign does V1 have and why? Yeah, because it's a virtual image, and then that's serving as a real object actually for the other lens. So one is minus the other. Yeah, so that's fine. And then if you stick all that together, let's rub this off rather than go onto a different board. Stick all of that together. So for your first lens, you end up with V1 equals n minus 1 over R1, and then minus 1 over V1 plus 1 over V equals n minus 1 over R2, and you add them together and hopefully you can see you're going to again recover the full lens equation as we know it. Okay, so this is maybe a nice way of thinking about it. It's actually exactly the same argument as the deviation angle one, but just described in different language, I suppose. This slide I do not need to go through because I've done it all. What the purpose of that slide was just to say a few words about the geometric sign convention, particularly noticing this minus sign that you might see in books. It's very common to see this form for the radii of curvature in books, and that just means they're using the geometric sign convention. Notice, so you might want to quickly make a modification. I think I wrote instead of this on your slides 1 over u plus 1 over v. I just changed it to be the more generic 1 over f here. The reason I changed it was because, well, can you tell me why it's slightly wrong what I've written on your slides? So I think I wrote that equals n minus 1 over R1 minus 1 over R2. So this is written in geometric sign convention, but that's actually written in real is positive on your slides, and so I did a mixed sign convention there. However, having said that, actually some books really do use this mixed sign convention, so I said it's all a mess, right? So I wrote something I didn't mean to write, but actually I also wrote something that you still might see in books. So what you've got to do is choose a sign convention you're happy with, and then absolutely stick to it rigorously, but then don't be surprised if you see something different, okay, in books. Okay, so that's it on lenses, just a summary of the different kinds of lenses you might come across. Obviously, you'll be very familiar with the biconvex, and that's what we've been drawing mostly. There's the biconcave as well. We've just been talking about the plano-convex, and also there's the plano-concave. And then these two, you may or may not have come across these. if you wear glasses or spectacles, these are very likely the kind of lenses that you have in your glasses. We got the positive meniscus, which is overall converging. What you can see, well, in both of these, the curvature goes the same way, but with different radii of curvature on both sides. So depending on those relative sizes of the radius of curvature, you'll either end up with an overall converging or an overall diverging lens. According to the formulae that we've written, you can work out, as long as you know the radii of curvature and you know a particular sign convention that works for you, you can figure out whether it's going to be converging or diverging. Okay, so that is it on lenses. We're now going to go on to mirrors and spend the rest of the lecture talking about that. So I'll just pause for a second in case there are any questions. I'll take a sip of coffee. All right. Okay, so mirrors. You will not be surprised to learn that we are going to work in the regime of completely wild approximations with mirrors, just as we have done for lenses. Okay? So we are again always going to work in the paraxial approximation, small angles. We are going to, I was going to say always, we're going to mostly assume spherical mirrors. There's a little bit at the end that I talk about non-spherical mirrors, may or may not get there today. So by spherical, I mean that this cross-section that I have drawn is the arc of a circle, okay, this 2D cross-section. And then we are going to introduce the thin mirror approximation as well. So what I mean by thin mirror is that the curvature is very, very shallow. So if you look at this point A, for example, you can consider this point A both to be directly above P, and you can also consider it to be a point on the surface, right? So that distance there is very small, and that's what we mean by the thin mirror approximation. Okay, so if we look at what's going on here, so as I said, that we're considering spherical mirrors, so this is the arc of a circle. C is labelled to be my radius of curvature, so this black line is a radius of that arc. Here is my light source. I've taken a particular ray. It's coming up here, bouncing off this point A. We're obeying the law of reflection, of course, so hence these thetas labelled on, bounces back, and it's going to cross the axis somewhere here. And we are now going to find out where it crosses the axis, i.e. we're going to derive the so-called mirror formula. And we're going to do that in the way that is kind of becoming hopefully quite familiar, that we're going to do the proof for one ray and then show that the answer is independent of the exact ray that I chose. Okay, so the writing in the box is something like 5 or 6 lines or something. So what to write here? Right, first of all, we're just going to do a little bit of geometry. So first of all, I'm going to write that beta equals theta plus alpha. So just make sure that we can all see that. So I've labelled on these alpha, beta, gamma. Beta is the angle between this dashed line and this radius. Okay, this, of course, this red, black, dashed, so if you follow it, is a triangle, so that angle there is 180 minus beta, and so we've got what I just wrote. Similarly, we've got gamma equals beta plus theta, and I can write that as alpha plus 2 theta from that. Also, I'm now going to just multiply this by a factor of 2. And then from that means that that is alpha plus gamma. So 2 beta equals alpha plus gamma. Right. Okay, so now we're going to use the small angle approximation like we always do. And so I can write that alpha is AP over OP, so it's that vertical distance divided by the object distance, I, it's roughly equal to the tan of alpha. Beta equals AP over CP. and I'm running out of room, but try and squeeze it in, and gamma equals AP over IP. Okay, so let's substitute that into what we've got. So we've got two lots of, AP over CP equals OP. Oh no, it doesn't. Oh, sorry. Right. Plus AP over IP. All my APs go away. And I'm also then just going to convert that. That clearly is just my object distance, more traditionally labelled as U, and that's my image distance, more traditionally labelled. That is not a divide sign. That's supposed to be a sort of bracket thing. Right? So what I've got is 1 over U plus 1 over V equals 2 over R, remembering that CP is just the radius of that, of the curve of the spherical mirror, radius of curvature. So I'm also just going to call that 1 over F, because then you can see that we've got something that is essentially the same as the thin lens equation. So that is the thin mirror equation for spherical mirrors. Sorry, was there a comment? Question or okay? Okay. So that's the thin mirror equation. So what this is telling us is that if I have an object spewing out light rays, it will be focused to a point on axis related by this equation, but that there is a very specific relationship between the focal point and the radius of curvature as well. In fact, it is such that F equals R over 2. So if I have, for example, a concave mirror like this, here's my light ray coming in, there's going to be my radius of curvature, there is the focal point exactly halfway, and that is the way that light will focus for parallel rays coming in. Okay. Right, so what we've just seen then is that a spherical mirror will form this point image of a point object according to this equation under the approximations we've used, which are the paraxial and the thin mirror approximations. So just the same as the lens formula, this equation can be generalized. So what I mean is the lens equation was valid for both converging and diverging lenses and for real and virtual images. So is the mirror formula, again, as long as we use an appropriate sign convention. We're still going to be using the realist positive sign convention, so the U and V are going to represent just as they did before, positive for real objects and images, negative for virtual. And then concave mirrors we will see usually, not always, but we'll go through that, usually create a real image. I was just drawing this diagram again, don't know why I did it again. Anyway, so that's a concave mirror, and they have positive radii, so R positive. Someone said something about 0. What? Is there a question? No, okay. Convex mirrors will form virtual images like that, and radius of curvature negative in our realist positive convention. Okay. Right, so let's look at this in a bit more detail, so how we figure out exactly where images are going to sit, and, their location and their size and so on. So we're going to do the ray tracing again, basically, but ray tracing for mirrors rather than lenses. But as you might imagine, it's very, very similar. And in fact, 2 of the 3 special rays are exactly the same. So here we've got a concave mirror. I'm just going to represent, this is supposed to be spherical, right? But I can't be bothered to draw that all the time. So this is going to represent a concave mirror with these the sort of head and feet sticking this way represents a concave mirror. So you've got to sort of remember that even though it doesn't look like it, a line going from C to this mirror is always going to be radial and therefore normal to the surface. So 2 of the rays are the same as for lenses. So there's one that here's my object, and there's one ray that goes in parallel, and it's going to come out through the focal point. And then there's another ray that can go through the focal point, and that will come out parallel. And already from these two rays, assuming that we believe all rays are going to focus in the same place, then we can already draw on where our image is going to be in this case. But there is a third useful ray as well. And whereas for a lens, it was the one that went straight through the middle of the lens, for a mirror, it's the one that goes through the radius of curvature. So, as I said, this ray is hitting the mirror normal to the surface, even though it doesn't look like it, because this is a radius of curvature. So it hits the mirror, and it bounces straight back. Okay, and it seems that I've drawn it correctly, so that they're all meeting at the same point, and there's my image. So let's just do a little calculation just to sort of make this a specific example. So in this diagram, I've put my object to be 3f away from the mirror, and we're just basically going to calculate the location and the size of the image in this case. Okay, so, I don't know, 5, 6 lines, something like that. Okay, so I'm going to use my mirror equation. And I want to find out v. So that is going to be 1 over f minus 1 over u, which in this particular example is 1 over f minus 1 over 3f, 2/3 f. So v equals 3 over 2f. So it's just halfway between in this particular example, okay, as it looks there. What's the size of that image? Well, magnification, I'll show why in just a second, but this linear magnification is exactly the same as for lenses. So in this case, we've got 3 over 2f over 3f, so it's a half. So we've got that our image is half the size of the object in this case. Okay, and this is true when you put your object outside of the radius of curvature, you're going to get an inverted and a reduced image. Why is that true? Well, maybe it's already obvious to you from that diagram, but one set of rays that is useful to see it, which I haven't drawn on there because it would have got too messy, is just that, so this is my mirror again. Let's give it little feet to show it's concave. Right, so if I have my object here, for example, and let's look at the ray that's going to come right into the centre of the mirror, and it's obviously going to come out at the same angle as well. That's supposed to be the same angle. And at some point, I'll have an image, right? So that is V, that is U. So this ray is just the one that's hitting the centre, coming out at the same angle. And so there, from similar triangles, hopefully you can see that just as for lenses. That's true. Okay, so in terms of magnification, and indeed the equation it satisfies, mirrors are very, very, very much the same as lenses in the way that they behave. Right. So that was an example where we'd put the object outside of the centre of curvature. Let's just to, be for absolute completeness, run through all the possible different examples that you might have, and draw the ray diagrams, just so that you have them all for reference, okay? So here's one where I put the object actually at the centre of curvature. So what's going to happen there? Okay, the first ray I can draw is going through the focal point, coming out parallel. Another ray I can draw is the one going in parallel and coming out through the focal point. I can't, of course, in this case, draw the ray that goes through the centre of curvature. I've just got those two of the 3 special rays, but that's enough. So I can see that my image is now inverted, but it's the same size. So just as we had like the concept of an inverting lens, we also have the ability to make an inverting mirror. If you put the object a little bit closer, so somewhere between the centre of curvature and the focal point, then you get this upright sorry, no you don't. Sorry, you get an inverted and enlarged image, sorry. Same 2 rays are being drawn there. And then if we move it to the focal point, then you get this quite nice, interesting special case of a parallel beam of light. So again, I've drawn the ray going in parallel and coming out through the focal point. I can't draw the one that would go through the focal point and come out parallel, but I can draw the ray that, as far as the mirror is concerned, looks like it has come from the centre of curvature. So it goes up and then bounces straight back through the centre of curvature. And you can see that those rays are going to be parallel. And then finally, for concave mirrors, we have the case where we can put the object closer. And this is the one case where, with a concave mirror, you will actually get a virtual image instead. So here's the ray going in parallel, coming out through the focal point. Here's the one that will bounce back through the centre of curvature. But of course, they're diverging on this side. But you can trace them back, as we did for lenses, and you get this upright and enlarged mirror. So this is how makeup and shaving mirrors work, those horrible mirrors where you just look much larger than you want to look. At least I do. There's far more detail than I ever want to see. So that is those kinds of mirrors. And then finally, we've got the convex type mirror, and these always produce virtual images. They're always upright and they're always reduced. So just to talk through these rays, because they look a bit messy, this is a bit more difficult probably to draw than for the concave. So here's, what's going on? Right, here's the one that's going in parallel, and it of course is reflected off, but if I were to extend it, then it would go through the primary focal point. Primary focal point is this side. Then we've got the one that would, if I traced it back, go through the centre of curvature. That's that one. And then we've got this one that would go through the focal point and is reflected parallel. I can really hear quite a lot of talking. If you've got any questions, let me know. The acoustics are quite such that I can really hear almost everything down here. So if you've got a question, please let me know. Have you got a question up there? Okay. Right. I think they are funny acoustics. I think for you guys, you actually can't necessarily hear each other as well as I can, actually, so I can hear pretty much everything, so just to let you know that. Right, so mirror sign conventions. So just quickly, I'm not going to go into this in quite as much detail as I did for lenses. Almost hopelessly confused. Right, so you've got choices to make, of course, the usual choices. Shall I use real as positive? Shall I use geometric? But actually, even in geometric, you'll find there are decisions to make. So sometimes, or some books will stick to a Cartesian coordinate system. So here's my mirror at x equals 0. And they will stick to that direction as being positive x the whole way through the problem. But then you'll find other books that will decide, well, let's follow the light path instead. So left to right is going to be positive until I hit the mirror, and then right to left is going to be positive, right? So you'll see all these different things. You've got the usual issue of shall I put a minus in front of the magnification or not, right? So there's at least these three places where arbitrary minus signs can creep in. In the end, you just have to stick with a sign convention you are happy with, and then work out what everybody else is doing if it looks different. Right, so I think I've got time to just at least do the start of this next bit, probably not to finish it. But I mentioned that I was going to talk briefly about another kind of mirror, other than spherical mirror. Mostly we're working in the spherical mirror approximation. But if you know anything about mirrors or parabolic mirrors at all, you'll know that actually it's a parabolic mirror you need to form a parallel beam of light. So we have just been saying, or I have just been saying, that we can form a parallel beam of light from a spherical mirror. You know, if I place a point-like object at the focal point here, the rays will come out parallel. And that was a spherical mirror. But actually, it's a very well-known fact, right, that it's a parabolic mirror that you actually need for that parallel beam. And in fact, you may have even done, you know, sometimes you can do those sort of experiments, if you can sort of stand at there's big parabolic mirrors, 2 of them, and you can maybe stand at the focus of one, kind of whisper, and your friend stands at the other focal point, and you kind of whisper, and then this beam of sound is travelled to them, and then focused back at them. And so you can speak really quietly, and they can hear you very, very clearly. And it's because of this effect that you stand at the focus, and the beam gets sort of bounced off both mirrors and then focused directly at the other person. So you might have seen things like this, or certainly you may have heard that it's parabolic mirrors that form this parallel beam of light. So if that's the case, what's going on? Have I been lying to you that spherical mirrors produce this parallel beam of light? Well, yes and no. I've been lying to you. You won't be surprised to learn that the answer lies in the approximations that we've been making. So we're going to, I don't think I've got time to do it in 5 minutes, probably the whole way, but what we're going to do first of all is just prove to ourselves that yes, it's definitely a parabola that we need to form a parallel beam of light. And then I'm going to talk about, probably next week, the approximations, what is it about the approximations we have made that actually make our system still behave like a parabola. Okay, so we can deduce the shape we need just from Fermat's principle, thinking of Fermat's principle. Right, we want to produce these, okay, here are our parallel rays, and these are the plane wavefronts that we are producing. Now, these wavefronts will be plane if the time that it is taken for the light to travel along any of these red lines that I've drawn is the same. So that's according to Fermat, right? Now, because these are all in air, I say the time taken must be the same, but actually that's equivalent to the length of all of these red lines must be the same, as long as we're in air. So let's just think about a parabola for a second and try and deduce that this is the shape that we need. So you will probably, when someone says the word parabola to you, you'll think of some sort of curve like this, right? Y is proportional to x squared in some way. Okay, but actually that's quite a new way, really, relatively new way of thinking about parabolas, only dating back to Descartes. So people used to think of parabolas as purely geometric, in a purely geometric way. So the way that we're going to think about it now is in terms of the locus of points. So for example, you'll be very familiar with a circle. That is, if I choose a reference point, a circle is the locus of all points that are a particular distance r away from that point. For an ellipse, I would choose 2 points, and I would add up the sum of these distances, and that's the ellipse. Probably not a very good ellipse, sorry, but that's the locus of the points where the sum of those distances is the same. For a parabola, we define it in terms of a point called the focus here, and a line called the directrix. And it is the locus of all points that are equidistant from this point and the directrix, by which I mean the shortest point. You take the shortest length. So, okay, so that point clearly halfway between them, that's on the parabola, and then it's going to curve up in some way like this, such that these distances d1 and d2 are the same. So that is how you geometrically define a parabola. Okay. So what I'm going to quickly do, can I do it in a minute? Let's try. I'm going to set up a Cartesian coordinate system. So y equals 0 is going to be at the bottom of my parabola. And I'm going to require that, in fact, d1 squared, just because it's a bit easier, is equal to d2 squared. So using this coordinate system, what I've got is x squared plus y minus a squared equals y plus a squared. So x squared plus y squared minus 2ya plus a squared equals y squared plus 2ay plus a squared. Some things are going to go away. And if I rearrange that, what I've got is that y equals x squared over 4a. So what we've done so far is just to prove that, yes, this geometric definition of a parabola comes up with the equation form of a parabola that you are used to. Now that actually, therefore, has told us that a parabola is the right shape. okay, because we have just defined it. We've definitely recognized this as being a parabola, so we know that this definition that I started with, this geometric definition, is the right one. And so what that is telling us is that all of these sort of lightish blue lines are the same length as the green lines, and therefore all of these lines, starting from the directrix, going up to the top of the red arrows, all of them are exactly the same length, meaning that a point source here will indeed form plane waves, right? So that's where we're going to stop now, having convinced ourselves that a parabola is the right shape to produce a parallel beam of light, and then next time I'll start with proving why our circular spherical mirror approximation is still giving that answer. Okay, that's it for today. Thank you.